Okay, so this is the 2014 January paper. A new type of insulating material has been introduced into the market. Your manager has asked you to evaluate the projected heat loss of the product. For the following data, calculate the heat loss of the material. Insulation sheet of dimensions 2000 mm by 1000 mm and thickness 100 mm and thermal conductivity of 0.025 watts per meter Kelvin. Take the lower temperature as -5 degrees Celsius and the upper temperature as 25 degrees Celsius. Okay, so the first thing you have to do is figure out what you're being asked to do. You're being asked to calculate the heat loss. Okay, and what information have you been given? Well, you've been given the dimensions, which are 2000 millimeters, so the 2000 millimeters should be in meters, so it's going to be 2000 by 10 to the -3 meters. Okay, and if you want, that's just 2 meters. So the 1000 millimeters is now going to be 1000 by 10 to the -3 meters, which is just 1 meter. And then the thickness is 100 millimeters, which is 100 by 10 to the -3 meters, which is 0.1 meters. Okay, now if we have dimensions of like 2 meters by 1 meters, this means this is giving us the surface area. And in a formula, it could be represented by the letter A. The thickness you may think could be represented by the letter T, but T could mean temperature or time, so generally T isn't used. Depth is another word for thickness, so it could be the letter D. We're also given thermal conductivity. Of 0.025 watts per meter Kelvin. And you may not know the letter for that, but the constant of thermal conductivity is given the letter small k. Okay, so this capital K is Kelvin and the small k is the constant of thermal conductivity. And two other things we've been given is two temperatures, -5 degrees Celsius and 25 degrees Celsius. Now they could be, generally if it's just one temperature, it's given the letter capital T. But here when we have two temperatures like this, they're generally called, one of them will be theta 1 and the other will be theta 2. Okay, so you're looking for a formula that includes the letters A, D, K and thetas. Okay, and that's the heat loss. Okay, so if you go back to the end of the exam paper, you will see a formula that is this. Q equals K, small k, capital A, theta 2 minus theta 1 all over D. So we've got the letters, for the numbers. We've got the numbers for the letters now, and Q should probably have a dot above it as the rate of heat loss. Okay, so now we can say Q equals K, which is 0.025, multiplied by the cross-sectional area, which is 2 meters by 1 meter, multiplied by the temperature difference, so we could say the 25 degrees minus -5 degrees. And it's all divided by the thickness, which is called the depth in this case, 0.1. Okay, so if I put this into the calculator, I am going to get 15 watts. And that's your answer. So the heat loss of this material is 15 watts. Alright, so then the next, let's see, part 2, 4A part 2. Here it is. And it says, a radiator of dimensions 1200 millimeters by 400 millimeters has water at 70 degrees Celsius flowing through it. If the emissivity of the material of the radiator is 0.8, right, if E equals 0.8 for this radiator, calculate the radiator's rate of heat loss. The owner eventually replaces this radiator with a chrome radiator with E equal to 0.04. Calculate the new rate of heat loss and advise the householder accordingly. And the Stefan Boltzmann constant is this, 5.67 by 10 to the minus 8 watts per meter squared Kelvin to the power of 4. So the temperature is measured in Kelvin. So again, we'll take out what information we have to get. The first thing is we have to calculate the rate of heat loss. So you know, it could be the letter Q, or he might just say the rate of heat loss. And I think in this one here, at the back of the exam paper, he gives a formula which says heat loss by radiation equals. So let's just take that down. Heat loss by radiation is equal to E sigma A capital T to the power of 4. So all you have to figure out is, well, generally you're going to have to multiply all the numbers because the letters are stuck together. So there's no dividing in this one, but you just have to find out what's what. So E stands for the emissivity. That's how effectively the material will release heat. That's going to be 0.8. There are no units for it. Z, or sigma, you may not know yet. A is a cross-sectional area, so that's going to be the 1200 millimeters by the 400 millimeters, but this is in millimeters, so we're going to have to change those units. The temperature is 70 degrees Celsius, but if you look at the formula or the units here, it's measured in Kelvin, so that has to become Kelvin. So it's going to be 70 plus 273. That will make that Kelvin. So that's going to be, if you were to add them together, that will be 343 Kelvin for the temperature. We can change these here. That's going to be 1200 by 10 to the minus 3 meters multiplied by 400 by 10 to the minus 3 meters. They're meters now, okay? Well, then that means the only number that's not accounted for that we're given is a Stefan-Boltzmann's constant. So then the sigma must be by default at 5.67 by 10 to the minus 8 watts per meter squared Kelvin. So all we have to do is convert the areas, make this look a little bit easier. So this here, if we were to get the surface area, it would be 1.2 multiplied by 0.4 meters squared. So now this, we can call this heat loss by radiation. Heat loss by radiation for the first radiator that has an emissivity of 0.8. So that's going to be 0.8 multiplied by 5.67 by 10 to the minus 8 multiplied by 1.2 multiplied by 0.4 multiplied by the temperature in Kelvin, 343 to the power of 4. And you plug that into your calculator and you should get 301.364 watts. Okay, so that is the rate of heat loss from this radiator. Now, the emissivity constant here is 0.8 and the emissivity constant for the second heater is 0.04. The emissivity constant ranges from 0 to 1. If it's 1, it means it radiates quite a lot of heat. Okay, radiates a lot of heat. Okay, so, and if it's 0, it doesn't radiate any. So then let's try for the other one. So then it's the heat loss for the second one. It's just going to be, instead of E being 0.8, we put in 0.04. All the other numbers we'll assume are the same. We'll assume the radiator takes up the same dimensions, and we're comparing at the same temperature, which is 70 degrees Celsius or 343 Kelvin. So it's going to be 0.04 multiplied by 5.67 by 10 to the minus 8 multiplied by 1.2 by 0.4 multiplied by 343 to the power of 4. Now when you calculate that, it works out as 15.1 watts. Okay, so, well, you can see anyway, as the emissivity constant of the second radiator is so small, it's not going to release as much heat. So now you have to recommend which radiator would you recommend to the householder? Well, a radiator is meant to radiate or release heat. So you want the one that releases the most heat, so that was the first one. So I would advise the householder not to change heater. To keep the old heater, as it radiates more heat. There we go. That's 4A done. Okay. So now then the next part, 4B. 4B, what is meant by laminar flow and turbulent flow? So, right. There's three types of flow. Laminar flow, well, roughly. Laminar flow, transient flow, and turbulent flow. The laminar flow generally occurs with thick liquids that move nice and slowly. So basically the molecules in the liquid move at the same speed and in the same direction. Right, so you can see that for laminar flow. Laminar flow. The molecules of the liquid, the fluid, move with the same constant speed in the same direction. So if you had to say this is a pipe, these are the vectors indicating the flow of the fluid. They're all the same length, they're all going in the same direction. Okay? Now, if you want to go into more detail, if you were to look at the cross section of the pipe, the flow right at the edges of the pipe will be slow or practically zero, and then in the center of the pipe the flow is much faster. So you would have a rim here of very, very slow in that circle, then another circle which is slightly faster, and then another circle which is faster, and in the center the flow would be fastest. Anyway, the other thing you need to know about flow is that for laminar flow, and this is the word, the Reynolds number is less than 2,300. Some people might say 2,200, 2,100. But anyway, the Reynolds number is the thing that is related to laminar and turbulent flow in your exam question. Right? So in turbulent flow, an example of laminar flow is just water coming out of a faucet or tap. Because when it's coming out of the faucet or tap, it's just all coming down straight. It looks like a pipe of water. It's all moving at the same direction and at the same speed. Okay, so then the next one is turbulent flow. And in this case, well, turbulent, as you've heard of turbulence, that will be quite disorderly and chaotic flow with a lot of eddies. So the molecules in the fluid move in different directions and at different speeds. They move at different speeds and in different directions. You can give examples. It's called eddies, two little whirlpools. It's chaotic, chaotic, or disorderly. Now this here laminar flow is quite orderly looking, you know. Okay, and in this case the Reynolds number for turbulent flow is greater than 4,000. Reynolds number, that's the word to do with this. Okay, what else about turbulent flow? For example, the back of a speedboat, you know how the water is very rough at the back of a speedboat, that will be a turbulent flow. The water at the back of a speedboat. Okay, that was worth 6 marks, and that is part 4B1. Yeah, okay then, so the next part is going to be part 4B2, okay, and this is a calculation, okay, and again we have to figure out, is it laminar or turbulent flow. Water is flowing at a velocity of 1.5 meters per second in an irrigation pipe of diameter 5 centimeters. If the coefficient of absolute viscosity is 0.8 newton seconds per meter squared, determine if the flow is laminar or turbulent. So that's quite a high viscosity, it's quite a thick fluid. Okay, so we could take out the information. Velocity is generally given the letter V, which is 1.5 meters per second. The diameter could be given the letter D, or capital D, and in this case it's capital D, okay. And it's 5 centimeters, which is the same as 5 by 10 to the minus 2 meters. There's the coefficient of absolute viscosity is 0.8 newtons seconds per meter squared. So, and we know it has to do with a Reynolds number. So if you have RE, so if you go to the back of your exam paper again, you will see a formula that has RE beside it. And that formula is rho V D divided by mu. Okay? So rho, this is the density of a liquid. Mu, this is the viscosity. V is the velocity, and D is the diameter of the pipe that it's flowing down. So we were given velocity, we've got the diameter, and we're given the viscosity. We weren't given the density, but the substance is water, and the density of water is 1,000 kilograms per cubic meter. DNSITY of water equals 1,000 kilograms per cubic meter, or per meter cubed. So now we have everything we need to put into this formula. So I can say the Reynolds number is going to equal rho, density of water, 1,000, multiplied by the velocity, which is meters per second, that's grand, 1.5, it's the right units, multiplied by the diameter, which we say is 5 by 10 to the minus 2, and that's all divided by the viscosity, or the absolute viscosity of the water, well, of the substance of 0.8. Okay then, so you put that into your calculator and you'll come out with 93.75. That's less than, a lot less than 2,300, so as 93.75 is less than 2300, the flow is laminar. And that's 4B2 done. Okay then. This is the last part of this question now. Right. So a sound has an intensity of 3.5 by 10 to the minus 4 watts per square meter when measured under certain conditions. Calculate the sound intensity of the sound in decibels. Note the threshold of hearing is I0, 1 by 10 to the minus 12 watts per meter squared. So the threshold of hearing is the faintest sound that a human can hear. Okay, so we have, if I0 is the intensity for the threshold of hearing, then more than likely a capital I again is going to be represent the intensity here. So that will be the letter in the formula. So we're looking for capital I equals 3.5 by 10 to the minus 4. And we have I0 equals 1 by 10 to the minus 12. And that's watts per meter squared, watts per meter squared. And all we have to do is get it in decibels. So if you look at the back, there are two letters that have, well, there's one formula that has I in it, and it's S-I-L. And that stands for sound intensity level. All the one phrase really, sound intensity level. And that equals 10 log to the base 10 of I divided by I0. Now this is a very, very quick question to do. So SIL, the sound intensity level, and this here will give it to you in decibels when you do this, okay? It's going to be 10 times log to the base 10, which is just the log button on your calculator, of 3.5 by 10 to the minus 4 divided by 1 by 10 to the minus 12. So then you put that into the calculator. So it's going to be 10 multiplied by this log here, because that's the log to base 10. Put in the fraction button, 3.5 by 10 to the minus 4 at the top, and below 1 by 10 to the minus 12. Come out of there, close the brackets, press equals, and you get 85.44 decibels. And that's your answer. 85.44 decibels. So you'd say D, capital DB. DB. I'll just don't be D. Decibels. I'll just write decibels. 85.44 decibels. Oh God, that's messy. And that's your answer, and that's the question done.